Hello and welcome. In this work example, we're taking a look at a turbine at a hydroelectric power station that is situated 30 meters below the level of the surface of a large lake. The water passes through the turbine at a rate of 340 cubic meters per minute. The overall efficiency of the turbine and generator system is 90%, so the turbine here is 90% efficient. And the density of water is also given, so I put it here in the lake. The density of water 1,000 kilograms per cubic meter. So from that given information, our job is to calculate the output power of the turbine. Starting with the definition of efficiency, you can kind of say, well, that's going to be the numerator here. So efficiency, let's remind ourselves, it's the useful output power over the total power in. So anytime we're given the efficiency, it's probably going to be true that we're going to have to solve for, one or the other of these. And the real work of the calculation is, figuring out, in this case, what's the total power in, since we're solving, the output power. So once we figure out this, it's just a matter of plugging it in here and then, solving for the numerator there. So what is the total power that goes into this? The 30 meters is a clue. We can say that's the height that the water has to sort of fall. So there's gravitational potential energy that all these water molecules possess up here, and we're sort of converting 90% of that potential energy into electrical energy in the turbine. So we have to calculate sort of what's the power here. Now, if you recall, power is the rate that work is done, or the rate that one form of energy is converted into another. And so, the work that we do in lifting something is its potential energy due to gravity. This flow rate, gives us the volume of water per minute. And so that per minute there is going to be our time, per 60 seconds. And so it's just a matter of sort of, calculating how much water do we really have if there's this many cubic meters of water, and that's the mass of water, per cubic meter. So we can kind of use density. So we just kind of put all the ideas together there and put the calculation guide. So the work that's being done, again, is the potential energy. So that's mgh over T. And what we're really given is the mass per time, sort of indirectly, right? We're given the volume per time, and so we can convert this into a mass using the density. G, we can assume that this is here on planet Earth, so 9.81, and the height was given as 30 meters. So it's really just sort of converting our flow rate, mass per time, from a volume, into a mass. And so let's kind of let the words, kind of guide your thinking there. So we have 340 cubic meters. I'm going to say per minute. I'm just going to convert it right now, per 60 seconds, right? So you know that to get watts of power, we need joules per second. All right, so joules of work per second of time. All right, since I want to cancel out cubic meters, I can put the density like this. There's 1,000 kilograms of water per every cubic meter, right? So if I have 340 cubic meters and I've got 1,000 times, that number of kilograms. So that'll give us kilograms per second, which again would be the units of mass per time. So once we've multiplied 340 times 1,000 divided by 60, that's going to give us our m over t. So we'll sort of multiply this. In other words, this calculation right here gives us m over t. So multiply that by 9.81, multiply it by 30, and then now we've calculated our total power in. All right, so remember that this is just to calculate the total power that comes from the gravitational potential. All right, so let's practice our mental math here, as I will do. Let's see. So what's 340 times 1,000? Well, that's easy, 340,000, right? Now let's go ahead and divide that by 60. Do it in your head. So I'm getting like 5,600, like the sixes repeat, I think. And then times 9.81 times 30. And now we've got the total power equal to, well, mental math here, 1667700. There we go. And because it's, well, let's take a look at the units here. So the meters cubed cancel. We have kilogram. Remember that 9.81. This is meters per second squared, or newtons per kilogram. Maybe it's better to think about it that way. Newtons per kilogram, and then this was meters. So the kilograms cancel. We get a newton meter, which is a joule, and a joule per second, which is a watt. All right, so that's the total power in. over the thing we want to know, the power out, and we know it's equal to 0.9, right? 90% efficiency. So we'll take 90% or 0.9 times this value. I'll do it in my head. And we get the power out equal to 1500930. So 1.5 million watts, 1.5 megawatts. Let's see if that's one of our answer choices. As you can clearly see, that doesn't show up on the screen there. All right, so how can we do this? Can I switch it up? Stand by. Flight squad. Maybe if I were to switch my screen over here. There you go, and you can see it on the screen now. 1.5 megawatts, choice B. And so we go ahead and select that. This has been another worked example with Dr. Schleitz. Still living the physics life. We'll see you next time.